All right, guys, big day. Say me sure that one. Please. Okay, when I say big day, I mean big day. Chain rule. All right, this is where what on earth is happening? That's crazy. Look at this. It won't stop scrolling. Okay, there we go. Okay, so chain rule. Okay. Now, guys, before I get into definitions, I'm on page 67. Before I do that, I just want to show you, give you a visual for what we've been doing compared to what we're about to do. Now, I haven't taught you anything wrong, but I've omitted something that isn't necessary with the work I've given you so far. So watch this. So here's what we've learned so far. I'm going to give you a couple of examples. And I'm going to put them side by side. We have done so far stuff like 4x cubed. What we're going to do today is a function like for something 2x cubed minus 5x cubed. I need you to think about this like this. Out of room. I want you to think about this like this. Okay? This is what we did before. Now, x is technically its own function. But if I were to say, what's the derivative of x, an x term, what would you say? 1, which is great if I'm just writing the number 1. But if I'm multiplying by that, multiplying by 1 doesn't change anything. You will see in a moment, that's why we didn't even acknowledge that on the work we did prior. Okay? Right here, if I were to ask you right here to take the derivative of this function, we know that we're going to go 3 times the 4 is 12. Copy the x down, decrease the power by 1, and we would be finished, right? But here's the difference. What you're technically supposed to do on a function when you take the derivative is identify what is going on with the function on the other side or on one side. Technically, over here on the right, this function is being cubed and multiplied by 4. So what I do when I take a derivative is I go, all right, let's ignore that function for the moment on the inside, and let's deal with the outermost function. And the outermost function is I'm cubing it. Okay? And I would go, all right, well, 3 times 4 is 12. Copy that function down. Decrease the power by 2. And that's what I did here, right? The difference is this. The chain rule states that you need to go back and link, that's the word chain, link this to the inner function. And the way you do that is by multiplying by the derivative of the inner function. Now, what I didn't do every single time I took a derivative, or you took a derivative on Friday, or whenever you did your homework, what I didn't do is go back and take the derivative of the inner function here, because what's the derivative of that inner function? 1. But had that derivative, that inner function not been a single x, whose derivative is always 1, and if that inner function had been 2x cubed minus 5x, 2x cubed minus 5x, or g of x, I have to link the inner function to the outer function. So here, to take the derivative, I would ignore the inner function for now, and I would do the power rule because it's the outer function. 3 times 4 is 12. Copy down the inner function, 2x cubed minus 5x. Decrease the power by 2. But that doesn't account for the inner function. So what do? I go back and link, hence the word chain, link the inner function to this by multiplying by its derivative, 6x squared minus 5. That, my friends, is the chain rule. The chain rule is essentially how you take derivatives of composite functions. We've already got a plan for when functions are added together. You take the derivative of each one and keep adding them. We have a rule for when they're multiplied by each other. First to second to first. We have a rule for when you're dividing them. Low d high minus high d low. What we don't have a rule up until this point for is what happens when a function is inside of a function. This that I'm pointing at is a cubic function, a polynomial, inside of another cubic function. This is a g function inside of a cubic function. These are all functions inside of functions. I want you to look at, on page 160, I'm on page 67, look at the definition right here of the chain rule. I want you to look at this bottom one. This bottom definition right here that I'm putting a star by, there's an inner function inside the g function. Do not confuse this with g of x times h of x. If I had a g of x times h of x, that's a function times a function. First to second plus second to first. This is a function inside the g function. What do? I start with the outer function. Just like in the example I gave you, I started with the cube. That was the outer function. I'm going to start with the outer function. And I'm going to ignore this part right here. So what's the derivative of g of blah? G prime of blah. That was like me saying, what's the derivative of blah cubed? 3 blah 2. I look at the outer function and I take the derivative of that, and notice that my blah just stays the same. You can see it right here. This right here represents like the h of x in this problem. That's the inner part. That's like a 2 h of x to the 4th. There's your h in the inner. What do? I look at the outer function first. What's the outer function in this case? The power rule. So I go power rule, 8 blah 3, 8 blah 3. Notice the h of x remains unchanged. 8 blah 2. No, 8 blah 3, sorry, because that's a 4. Notice the h remains unchanged in the first part, right? And what does that do, this step? It takes the derivative of the g part, just like what did this do right here? It takes the derivative of the 4. And by the way, the constant could have just been brought down. There's the 2, 4 blah 3. The 2 and the 4 just got multiplied together. So we don't consider a constant out front a function. We just drop it. Now, then what do based on this rule? I link the inner function to the other part by multiplying by the derivative of the inner. So whatever the inner part is, I take the derivative of that. Whatever the inner part is, I take the derivative of that. That is the h prime of x. Are you seeing this a little bit? Now, it's not always going to be written with g and h's, although in AP Cal, a lot of times it is. All right. So a lot of times it might be written like that. Well, just look at this and go, all right, I'm going to ignore this. I'm going to take the derivative of the g. G prime, copy the blah down. And when you do that, you have taken the derivative of the outermost part. Put a times in there, go back, take the derivative of the innermost part, and multiply that to the original part. And you'll see this over and over and over. And it's not just power rules. That's just all we know right now. But by the end of the day, we'll know a couple others, and you can see how that plays out. All right? So if you ever look at something, and it's not just a single x, whose derivative is 1, and it's something else that's being raised to a power, or maybe you're signing a big function, or maybe you're taking the natural log of an ugly function. That's a function inside of a function. So you look at it and you go, well, what's the outermost function? That starts the problem. And you consider the innermost stuff blah. And you'll hear me say blah a lot. I'll say, look, that's blah to the fifth. Homer says stuff to the fifth. Don't say either when you go to college. If anything, say, oh, that's an inner function H or an inner function U. Colleges use that a lot. Anyway, whatever. So let's look at a couple of examples. This is yesterday, 3x to the fourth. All you did was go 12x cubed. What we didn't do is then go back, because technically what I did, there's my inner function, and I'm raising it to the fourth. So outer function is power, 4 blah 3. So 12 blah 3. That's that. That takes care of the outer part of the function. Then I go back and take the derivative of x. But what's the derivative of x? 1. So why ever write dx? And why write times 1? It's not doing anything. But it does do something when that part right there is a different function. So what do? I look at the outermost function first, which in this case is your power. So 12 blah 3. That's the first part, and your outer function is dealt with. Then you go back. Don't ever write this second step I'm writing here. Go back and take the derivative of this. I never write that step. I go 12 blah 3, copy that blah down, and then the derivative of the blah, 8x minus 5, and you link them together with multiplication. You with me so far? All right, let's apply what we know so far to these first couple problems. I already did number 1 there for you. Look at number 2. What do you see right there? Number 2. I see on the inside a 4th degree polynomial, and then that function is being raised to a power, 4. So I see a powered polynomial. What is the outermost function? The 4. So here's me. I am treating this inside part like a blah. I'm literally thinking 3 blah to the 4th. Well, what would I do to take a derivative of that? I'd go 12 blah cubed. So I just copy down the blah, not doing anything with it. And what does that do? That's the derivative of the outer part. Takes care of the 4 and the 3. Now I go back, link the derivative of the inner part to it by taking the derivative of it, 8s minus 20s cubed.
What do you mean you have to link it to the?
What do you mean?
What do you mean by like linking?
I'm connecting it to this, linking it. I'm using the word link because it's a chain.
Right.
But you're connecting it to this through a product. And by the way, if you're ever looking at this, remember, these are all tricks we've learned, right? If you really wanted to know how to take the derivative of this, you would pull out your limit definition, which I'm not going to say because you're taking the limits test, but you would pull out your limits definition, the old ugly one with the F's and the H's and the zeros and all that junk. You would pull that out and plug in your so-and-so and plug in your whatever and do the subtraction, clean it all up and cancel the stuff out, factor it and cancel again, and then run your limit to get your function. We don't want to do that. The chain rule was somebody noticing, wait a minute, if I could make a substitution at the beginning and replace that other function with u, I know how to take a derivative of a u, f of x. So I have, which is also a trick. I'm going to use that, and then when I'm done, I'm going to go back and plug the u in. But this is the process by which that works. And there's a proof to all this. It's just not a part of this course. All right, jump down to number 4. I'm going to skip around a little bit. Look at number 4. Number 3 is just like 2 and 1. Number 4, what do you see? I see a what? And a fraction. To take a derivative of a fraction would require a quotient rule, right? But I also see that entire fraction being raised to the 3rd power. That's 2 functions. One function is cube this. One function is divide those 2 things. This is a function inside of a function. So ask yourself, what is the inner function? What's the outer?
The inner is the rule, the outer is.
And we always start with the outer because the chain rule says, and if you go back up here, when you have a function inside of a function, begin with the outer, take the derivative of it, and just copy the blah down, and then multiply by the derivative of whatever the inner part was. So check it out. Here's my fraction. So for me to take this derivative, f prime of x, I'm going to treat this fraction as like a blah. So all I'm seeing in my head is blah cubed. How do you take a derivative of a blah cubed? 3 blah 3 blah squared. Isn't that what you would do with the power rule? Bring down the blah. And I have not yet taken the derivative with respect to that. That takes care of the f on the outside, the function on the outside. Then you join it or link it by multiplication. By what?
Multiplied by the
The derivative of the inside part. What's the derivative of the inside part? Next, what do I have to do? Low d minus I over low squared. So low times the derivative of the high, which would be a 2, minus the high times the derivative of the low, which would be a 1. You don't have to put it times 1 ever. I'm just showing you my work. Over the low squared. And we don't need to simplify any of this junk. I mean, if we did, we'd end up with an x plus 2 to the 4th on the bottom and all kinds of a mess on the top. We are not doing that. Okay, so we'll just leave it like it is. We good so far? Okay, and number 5 is just like number 4 for the most part. Now, one thing I haven't talked about is these constants. I keep saying constants aren't functions, and you're like, well, why not? Well, if I treat a constant like a function, because technically it is, think about it. What do I now have if I treat 4 like a function? I got a product rule. Well, what happens when I go first d second plus second d first? That whole other part goes away, right? So all I end up with is this. If on my derivative, if my second d first makes it go away, then look, this is all I have left. First derivative of the second part, which is 5 blah to the 4th times the derivative of the blah, right? First d second, we already just said that plus second d first is going to go away. Didn't I just basically drop the 4 down and do the power rule? That's why constants, if you want to go 5 times 4 is 20, great. That's what you end up getting. It looks better than that, more simplified than that. But technically, constants, if you're ever wondering about them, drop them down, put a times, go about your business. Like I have people all the time, they'll see a problem like this. Y equals 4 square root of x. And they're like, wait a minute. I know how to take a derivative of a root x. The derivative of that is double that on the bottom and put a 1 on top. We'll get more into that in a second. What do I do with this 4? Well, a couple options. One, drop it down and just look at the other part. And the other part says double that on the bottom, 1 on the top. So you end up getting 4 over that. Okay, so you, again, if it's a constant, you can drop it because who wants to go first d second, right? Plus second d first. Oh yeah, that goes away every time. I don't want to treat it like a product. So the net result is you get first d seconds when it's constants. Yes, unless it's just obviously a power rule, and then you can drop it and multiply all at once. All right, let's jump to we got to go to the log rules. Okay, 2 rules I'm going to introduce, and believe it or not, these rules with exponential functions and log functions will be all the rules for logs that we'll have on this test. The only, and if you think about it, what else is on the 19 basic functions? Other than trig functions, what do we have? That's a good point. We will cover absolute value next year. I don't think we cover that this year. Square roots are powered functions, x to the half. Curved function, powered function, up to the 2/3. Logs, which we're going to talk about in a second, exponential. And everything else is like parabolas, lines, and so like polynomials, powered functions. So everything we have has been covered after this stuff right here, with the exception of trig. We're going to do a second test on trig functions. We'll basically introduce them, talk about more of the same, have a second test. You might be the one person who makes a D on it because I always seem to have one bonehead who doesn't do work. But the vast majority, my class average has always been an A as a collective class, and usually a strong A for both tests, with rare exceptions, maybe an 89 here or there, but overall it's been an A. All right, so let's talk about these last couple rules. All right, I want you to look at the E one. Now this says, okay, there might be something in for that U, but ignore that for now. what does it look like I'm doing to take the derivative of the g in that first step? What does it look like I did to go from e to the u to this next step? What does it look like I did?
Multiplied by 3.
That sounds like the chain rule. What did I do in the first step before the du? What does it look like I did to go from there to there?
You copy.
I copied the problem. If you ever see an exponential function, you will always take that. Now, I'm not talking about if it's added to something. If it's added to something, we know we do each one separately, right? If it's multiplied by something, we do a prime. But if it's just an exponential, you copy it down. No matter how ugly it looks, you'll see that in a second. Now, what is times the derivative of the exponent? That's the chain rule. That's saying, hey, if there's anything other than an x up top, that's a function inside of that e function. Didn't the chain rule say you got to go back when you're done and take the derivative of whatever that function was inside of it and link it to it through multiplication? That's the chain rule part. Okay?
Why is the exponent considered inside the function?
Because e to the x is a basic whole function. If it's e to the 4x squared minus 5x, now I have a function inside of my e to the x function. E to the x function is the basic e function. The derivative of e to the x is e to the x. But the derivative of e to the blah is e to the blah times whatever the derivative of that blah is. Okay? So if e to a power is a function, but e to a power, anything other than x, requires a chain rule. Just like x is a function. X to the 5th is a powered function, but anything else to the 5th is a function inside of that. All right, now, careful. AP Cal does not make you know how to take a derivative of exponential functions unless the base is e, but college does. So I can't speak for Helmers, I have always made my students know how to do both. Now, the vast majority of what we do in this class will not have bases like 2 to the x or 7 to the x. They'll be e to the x. But I do want you to know the rule. Here's the rule for this. Now, I want you to look down here where I'm pointing. I want you to scribble out what I have here, and I want you to write it in a better order. This is the way I want you to write. So right here, I want you to write a to the x ln a. And then I want you to put dx. Now, what's the difference between this that I'm underlining right here and this that I'm underwriting right here? Sorry, scribble that part out. What's the difference between this to here and this to here?
You kept it, except you also put a natural log
Of what?
of the base.
So I still copied the problem down, but I wrote natural log of the base. Why don't I have to do natural log of the base up here?
That's one.
Because it's equal to 1. So I did do natural log of the base. I just didn't bother writing it. ln of e is 1. I don't need it. ln of a is not 1, unless a is e. And then once again, what did I finish off with? The derivative of whatever the power is. In this case, the derivative of x is 1. So I don't really need that. But if that x had been x squared, the derivative of that's 2x. If that x had been 5x cubed minus 4, that dx would have been something else. But this du and that dx, that's the chain rule when you're done, if that's anything other than a single x. And if it is, I should have made that u. If it is a single x, I don't need to bother with that because dx is 1, right? dx is 1. I would not, this is terrible. I need to go back and redo this. dx is equal to 1 there, so I don't need to bother. Are you with me on this? Now, natural log. Take a look at the natural log. I want you to look at this, and you're going to rewrite this also. I want you to look at this. What does it look like I did to the natural log function right here? What does it look like I did to the natural log function to go from here to here? What did I do? And again, if you're like, why does this work? It has to do with the limit definition, somebody taking that limit definition using some very creative math, by the way, with natural logs and converting it into something else. Stay with me, and I'll tell you. What does it look like I did to go from natural log of blah to 1 over blah? Like, how would you describe that to me?
Well, it's like,
Divided the derivative by the variable expression.
Just the stuff that I circled. Does it look like I even took a derivative of anything? It looks like I just took the u and did what? Listen, put it on the bottom. And what happened to the log? Went away. Literally, that's what you're doing. If you are natural logging something, all you have to do is take what you're natural logging, throw it in the denominator. Why? Go look at the limit definition. It's terrible. I don't even bother teaching it. I will show you what it is with the trig functions. I go through a couple just for you to see it and go, oh, wow, is this what you really had to do on all these other ones? Yes, it's awful. Not awful like what we did when we showed the examples with polynomials. I mean, like truly awful, like really terrible looking proofs. One of them pulls out the sine of alpha minus beta and does all kinds of manipulation. Horrible. And limits are all over the place. Like you're getting kicked in the teeth. We're just going to know our rules. All right. So literally that is all you do. But what happens if it's not a single x? Then you go in the chain rule and you say, well, whatever I was logging, I got to make sure I take the derivative of that. So technically the rule is 1 over u. Chain rule says du. I don't like writing 1 over u times du because where's the du going to end up when you multiply it by a fraction? In the numerator. So all I remember is this, to take a derivative of a natural log of blah, copy the blah to the bottom, take the derivative of the blah on the top. And that takes care of the function's derivative and the chain rule all at once.
so natural log equals 1 over u, is that true for anything?
No, natural log of u does not equal 1 over u.
It's 1 over
The
u.
derivative of natural log of u is 1 over u. Right? The derivative of this is this. The chain rule says that. The derivative of this is this. The chain rule says that. And then simple math says you're going to end up with a fraction. These are derivative rules. Okay? So let's see how that plays out real quickly. Jump to number 6. So if I am natural logging blah, what is the rule for the derivative of a log, of a natural log?
1 over.
So I am going to copy that to the bottom. And literally, when I do that, I have taken the derivative of the natural log. Now, yeah, there's a 1 on the top, right? But that's me taking the derivative of the natural log. But I haven't addressed the inner function yet, have I? So the chain rule says, now multiply by the derivative of this, 6x minus 2. I just don't like writing it like that. So here's what I do. What I do is in one step, I go, oh, natural log. I know how to deal with natural logs. The rule is to just copy what I'm logging in the bottom, take the derivative of the bottom on the top. That's what this ends up being anyway, and I'm nice and neat and done. You with me?
Yeah.
Okay, exponential function. Look at number 8. What's the rule for e to the u, e to a power? What do I do to take a derivative?
Oh, well, that expression is inside the e function. So you do e first. You just copy it down.
I copy the whole thing down. That is literally what you do to take a derivative of an exponential function of e. Copy it down. But when you do that, you're taking the derivative of e to the blah. Well, I've done that. But I still haven't taken the derivative of that inner function, right? That function inside of the e function. So I go times. Now, again, when you multiply, you're multiplying by this whole thing. Don't multiply the exponent by it. Times the derivative of that, which would be what? 6x squared minus 4. You with me?
Yeah.
That's natural log and e. Now, scroll back up. What happens when it's not natural log? And we've already talked about exponentials like this. The only difference is, and I even told you to rewrite it, right? I said on one of these, don't write it like that. Just remember, if the derivative of e to the u is e to u, take care of the chain. Then the derivative of a to the x is a to the x what, though? natural log of the base, take care of the chain rule, the dx. So if that x was a u, you're going a to the u, ln a, derivative of whatever that u is. All right? Where do we see that? Look at number 14. So what is the rule for the derivative? No, it's not 14. We'll do 14. 14, how do I take a derivative of f? What's the rule when you see an e function? Copy it down. So I am copying, I'm really just dropping 4, and then copying the whole thing down. And that takes care of the constant and the outer function. I know it doesn't seem like the outer function, but it's e to the something. The something's the inner. The e is the whole thing. I'm done with that. Now what do I got to do?
How do you do
To take the derivative of the blah, right? How do I take the derivative of the blah?
the power over?
I got to, it's basically, this is like an embedded, this is like an f of g of h. So I did the outer one, the e. Then I'm going to do the next outer one, which is the 6. So 6 blah 5. And that takes care of the 6. And then I'm going to do what? The super ultra inner one, which is that 8x cubed minus 5. But look up at this. Don't look at your answer. Because you know why I don't look at my, I see people all the time, they go, all right, take a derivative, and then I take the derivative of that, and then I take the derivative of that, and then they go, and then you take the derivative of that, and then you take the derivative, and they just keep going. No, we're looking at this. Outer function, that's my e. 6 blah 5, that's the 6. 8x cubed minus 5, that's that. And when I'm out, I'm out. Now, what about 16? 16 is going to look exactly the same with one small change. 16 is not e to a power, is it? It's 3 to the power. Everybody with me? So right here, the derivative of f, where do I start? It's exponential. Copy down the whole thing. So 2 times 3 to the blah power. But what do I have to remember when I have a base that's not an e?
Natural log.
ln of 3. That is part of the exponential process. We just don't have to put it when it's a base of e because ln of e is 1.
Just the base, not the whole thing.
Just the base. And that gets rid of your constant, which technically I just dropped. That gets rid of the 3 part. The base, that's the exponential part. Now what do I got to do though?
Derivative of the x.
And the derivative of that is 8x minus 3. Now link that to the other part through multiplication. And that takes care of that. All right. All right, now look at the log. Go back up. Look at the natural log and the log. So this was natural log, and we said the rule was copy it to the bottom. Chain rule says the derivative out to the side, which is technically on the top. Done. What's different about that and a log that's not a base e log? Look at the answer. What did it look like I did? Oh, by the way, you don't love the way we did this here. I don't know why I did that. I have grown, but I keep forgetting to go back and change everything. So this is what I would do now to really explain it. Technically, the derivative of the log, and I'm going to even put a u up here. Here we go. Let's really make this good. Scribble that out. Put a u there and a u there. U there, u there, u there. So what do I do first based on my log rule? I copy whatever I am logging. Copy that to the bottom. Now, there's one difference here, like there is with a base that's not an e. This is a log that's not a base e. Instead of, though, multiplying by a log of the base, I am going to divide by a natural log of the base. That's the only thing different. Right here, check it out. I copied the u to the bottom, done. Here, I copy the u to the bottom, ln of the base. Now, why do you think I didn't have to divide by the ln of the base here? Because dividing by ln e is a 1, and I don't have to bother. But here, it's not a 1. And then what did I do to finish it off? Times the du. So what do you essentially end up with? Just a du on the top and a u ln of a on the bottom. So let's go take a look at that. Down, below. Find one that works like that, which is here on 15. So I look at the natural log and I go, wait, natural log, not available, but I do have a log base 4. So what are my log rules? Take this derivative. I recognize that normally the log rule is copy what I'm logging to the bottom. Great. But because it's not a base E, what do I have to remember? Do a natural log of that base and put it on the bottom. And by the way, people forget, wait a minute, is it the log? Does the log multiply by ln4 or divide by ln4? Does the exponential function multiply by ln3 or divide by ln3? Just remember, is there even a fraction on an exponential one? Then don't try dividing. Is there a fraction on a log one? Then definitely divide. So on where exponentials will multiply right here by ln3, these divide because these have fractions. It makes sense that they would go on the bottom. And again, this is just a trick. And then how do I finish this off? The derivative of the blah, which would be 2 blah, blah, blah. But where's the nicer way to place to put it? Just put on the top. So I finished up with 2 x cubed minus 5x to the first times, because of the chain rule again, 3x squared minus 5. Now let me show you a little trick with logs. Everybody looking? If you don't know this trick, it'll cost you. On a test, I will say, find the derivative, simplify completely. On an AP test, it'll just be multiple choice. And if you don't simplify, you won't see it. Does anything cancel here? What would have canceled? Tonight, you don't have to, but
X cubed minus 5x.
so you can see that this x cubed minus 5x, there's one of those, right? It's going to cancel with one of those. So your net result would be 2, 3x squared minus 5 over x cubed minus 5x times ln 4. Looks a little better, not a lot better. And I guess I could multiply the 2 in at this point also. Now, don't you have a log rule that allows you, not a derivative rule, but a logarithm rule that allows you to do something with this? What's it allow you to do?
Put it in the bottom of the.
Swing it out front. This is not a derivative rule. This is a log rule, right? Won't that keep you from having to do that chain rule at the end? Now, how do you take your derivative? Drop the constant. Takes care of that. What's your log rule? Copy that to the bottom times that ln 4. That takes care of the log. And then the chain rule just says derivative of your blah. Don't have to simplify a thing. My advice is when you're taking derivative of logs, before you get started, swing that out to the front, and it's one less step you have to have and much less complicated answer that you have to simplify. You tracking? All right, let's look at the chain rule a couple of other ways. Look at number 13. So 13, you have a log rule. What could you do?
Swing the 6.
Ooh, I could swing that 6 to the front and make it a what? Notice I'm not taking the derivative here.
18.
And now I don't have a power to contend with. One less thing that makes my life easy. Now, how do I take my derivative?
Derivative of
Copy the 18 down. It's going to be in the numerator. What's my log rule say?
18 times. Or it'd be derivative of x over x.
Okay, so you're copying that jump to the bottom, which is you're saying x, but function, whatever blah is, you're copying that to the bottom. And then you said dx, but it's d function, right? The derivative of that function on the top would be 24x cubed minus 9x squared plus 2. And look, there's nothing for me to cancel or simplify. Like there would have been had I not done that.
Wait, I don't get that because so the 18 is just like
Watch, I'll do it the other way. Can't you also swing this 3 up here and get this? Isn't that also true?
Yeah.
Let's try the derivative. So the derivative says there's no constant, so you don't have to worry about that. But you do have to copy down the entire blah. 6x to the 4th minus 3x cubed plus 2x to the 18th times ln of e, which you don't have to bother with. And then what do you have to do? That takes care of this. Now I got to take care of that.
Wait, but isn't the bottom like? I thought it was derivative of blah over blah, right?
Yeah, I haven't gotten to that top part yet.
But isn't blah just what's inside the parentheses?
No, blah is whatever you're logging. Look at your notes. It says LNU. It's whatever you're logging. It could be ugly. It could be simple, but it's whatever you're logging. It's not what's inside whatever you're logging. It's whatever you're logging. I'm logging. So my U is all of that to the 18th. So the derivative of all of that to the 18th ends up being 18 blah to the 17 times the derivative. That takes care of that. Times the derivative of this. This is something I didn't have to do the other way, did I? I didn't have to do this long, ugly power because mine didn't have a power on it. But look at that and look at this. They look significantly different, don't they? But take a closer look. There's the 18. And how many of these cancel? 17 of them cancel. And all I have left is that and that.
Got it.
So I think if you think about the process, that's a much uglier process than this. And you're not finished. You'd be fine on my test unless, which I do, when I ask you this, I say simplify completely. Which means, if you want to multiply 18 and you can, I don't make you do that. But I meant get rid of all this extra junk. But you don't have to get rid of it if you just swing that to the front and rewrite it because you don't have any canceling if you do that first, which is what I always do when I'm dealing with logarithms and I'm taking a derivative. All right, last couple, 15. Have I done 16? I've done 15 and 16? Oh, okay. So let me go back up. I saw one of these I have not gotten to. Look at number 11. So number 11, that's technically a power, actually, well, I'll do number 11. Number 11, that's actually a power rule, but we didn't memorize any rules for a 4th root, so I would just rewrite it as a what? A 1/4 power. So what is my derivative? 1/4
times
blah to the subtract 1, negative 3/4. And what does that get rid of? The radical. I've taken the derivative with respect to the radical. Now I go back, take a derivative of the inside part. 3x squared minus 4x, period. And that takes care of the inside part. Outer function, inner function. Now, check this out. Okay, go to the one that has the square root in it. I think there's one. If there's not, I'll have to make one up. No, there's not. All right, we're going to make one up. We're going to call this number 12b. So we're just go a little bit. There's a little room there. Go to 12b. So what if I gave you this function? F of x is the square root of 3x squared minus 4x plus 1. Now, we already said if I have an f of x that's like a square root, what was our trick?
put one on the top, but twice the.
Double it on the bottom, right? Now, here's what I didn't tell you. Go back and take the derivative of the inside part and multiply that out to the side. It didn't affect you here, did it? Here it does, because the derivative of the inside part's not equal to 1. But it's still the same process. The derivative of this is double that on the bottom. That's the rule. But technically, I'm now taking the derivative of the inside part and putting it out to the side. But why put it out to the side when you can just put it on the top? So I kind of skip that step and I end up here. Now, every year I have one or two very stubborn people when it comes to square root. They're like, I refuse to learn this trick. And they do this. Give them the same problem again. They'll say, oh, that function, I could rewrite it as a 1/2 power. Now, Here's what you would do if you rewrote it like that, and just look at your answer. 1/2 3x squared minus 4x plus 1 to the negative 1/2 to the negative 1/2 times 6x minus 4. They look a lot different, don't they? They mean the same thing. This is a square root function on the bottom. This is a 2 on the bottom. There's that on the top. They mean the same thing, but you tell me, if this was my derivative, and then I said, hey, find the derivative at 2, would you rather plug a 2 in there, or would you rather plug a 2 in there? I really don't want to plug a 2 in there and then have to deal with that fractional exponent. If I plug a 2 in here, worst case scenario is I end up with the square root on the bottom that I could rationalize, but calculus doesn't even make you rationalize. I'm really just done. I just simplify it and I'm finished. Here, I got to start thinking, wait a minute, what does a negative 1/2 power do? Oh, it's a square root on the bottom and blah, blah, blah. Just don't do this. Memorize the rule. And by the way, what if there was a 5 out front? What do you do with that? Drop it down. When you drop it down and put a times, doesn't that essentially mean it just ends up in the numerator with the derivative, with the chain rule part? So on these, I drop the 5 to the numerator, copy that to the bottom and double it, derivative of the inside part on the top. Guys, it's a lot I've thrown at you on chain rule day. I don't have any new derivatives to give you until this test, which is on what? Monday. So for the next, you're not here. Oh, here's something I might do. I haven't thought about, but I'm processing it. Tomorrow, you will be in this class. Okay. I had planned on just saying, do your homework from tonight, tomorrow. I think that might even say that on.
It says, there's like another homework.
Not for Tuesday night. What's it say?
There's a chain rule homework, or is this?
The other two go to tonight.
And there's
Yeah,
another.
but for right here, I said, on Tuesday, it says, do your homework from last night. Do me a favor. I mean, ultimately, if you don't have it ready tomorrow, I'm not going to take it up because of that. I might take it up later, but I might teach tomorrow. There's a chance on Thursday, I might take a half day. Okay. Like a half personal day. If I do that, I won't be here for you in the day ahead. I won't lose a day with you guys. So if we teach tomorrow, you guys would just have off Thursday afternoon. All right. Y'all are like beat down today, aren't you?
Yes.
I had a kid. I had a kid in my class named Bart. That's a good pull. Second year. Bart, I will not remember his last name. So funny. I love this guy. But he struggled. Second period, third period, something like that. And he was like, just always struggling. One day I'm teaching, I look up and I'm like, dude, where's Bart? He's just gone. And this girl behind him goes, dude, got up. He just gave up. Got up while I was teaching on the board. I guess I probably looked at the board too much and wasn't like flipping back and forth. Laid down, took his coat, made a little pillow. Dude was out. Just laid down on the floor. I'm like, what are you doing? That same class, have I told you the toaster strudel story? That very same class, I'm teaching one day and I hear this ding. What the heck is that? I kept teaching about 6 minutes later. Ding. What on earth? Third time the ding goes off, I'm like, are y'all not hearing this? And this guy goes, yeah. And I'm like, what is that? And he goes, toaster strudel? He has brought a toaster oven into the class. It's plugged into the back wall, and he's making toaster strudels for the class. How I didn't smell him, but he's like cooking toaster strudels in the back, passing them out. I'm like, what do you even do with that except go, bravo, bravo. I mean, creativity, it's not against the rules, a little bizarre. So funny. Anyway, y'all have a good one.
Figure someone from fourth period. Usually get to be about 8:06. Like, they would, like, if we're not gonna see it,
Wait, do you think that homework's due tomorrow at 6 a.m.?
I would guess so.
Really? Why from 48?
Because that's when she gets to school.
Why? Catching him out of that.
Yeah, I wish you would make it through on Wednesday.
Yeah. I don't, it said like use text contextual, but
It's just like this, the slide, it's like
Yeah.
13 through whatever. Unnecessary.
See you, man. Have a good one. Will.